felt from my time as a postdoc at MIT with Ronit and Piotr. So first I want to thank Ronit for probably more things than you know. So actually growing up, sorry, so this is okay. So actually growing up, I wanted to be a medical doctor. I think it started somewhere. I used the costume, I dressed up in one of the Purims as a doctor, and then like my Jewish mother was talk up. Okay, you know, my Jewish mother was really happy about it, so it's kind of it was always known that I'm going to be a doctor. But then I had to join the army, and this was this special program when you study math and physics at Hebrew University. So I actually did that because my Jewish father said, no, don't become a doctor. That's much better. So I went and did that. But then I said, okay, but wait, I wanted to be a doctor, so I have to kind of, so I quit that program and I went and studied medicine for 3 years. But kind of during like the studies in the third year, I said, well, but actually studying math was pretty fun. So during the third year, I said, okay, let me just try to take a few classes to finish that degree. But then the two first professors I had, I just took 2 classes, and it was Ronit and Noga Alon. And that kind of summed it up for medicine, because that was so much fun this semester that it had no chance. And then thankfully, I came here. So, and this is joint work with, ongoing work with Ronit. So that's the first thing. And the second thing is I actually need to thank Ran, because then the following year I took his class, and there was this really nice person there, and Ran gave really hard homework, so I had to work with someone, and that came out well. So, so thank you, Ronit and Ran. And then, of course, thank you for Piotr and Ronit for having me as a postdoc at MIT and hosting me for really, most of the time was fun, some of the time was COVID, but it was a great few years. Okay, so now back to the, and not actually for the most important thing is I think we need to thank Ronit for this community. So of course there are all these amazing ideas and amazing models and amazing mathematical results, but I don't think we would have gotten here if it wasn't for the great atmosphere and the vibes of this community. And I think a lot of this is thanks to Ronit, because so much of us came through her, like not as students or with her at contact. And I think she has good senses in choosing good people. And I think that's what makes this community so special. Great, and allow for collaborations and really friendships. And so thank you, Ronit. And I don't know, this is from recent years, so I don't know if it's because she's shy, maybe show it, but that's, but that's Ronit. No, I'm sorry. So thank you so much for just for this community, for this entire area. Okay, so now for the talk. So I'll talk about edge sampling, and if you are on Monday, then don't worry, it's the continuation of that talk. So it's still, and if you want, it's also good. So the goal here is to select edges from the uniform distribution. So we have a graph, and we want to be able to select edges from that from the graph uniformly, almost uniformly at random. So is going to be the n is going to be the size of the graph, and m the number of edges. And that's what we want. We want the algorithm to output an edge, so that each edge is output with roughly probability 1 over m, 1 over the number of edges. And of course, there's a lot of the works. Why do we need this this algorithm? It came from a model that Ronit came up with, which allows for, so most of the time, like the basic model was for sampling uniform vertices in sublinear time algorithms for graphs, sample a uniform vertex and maybe sample a uniform neighbor, or check if there is an edge. This is when you access either the adjacency list model or the adjacency matrix. But of course, Ronit won't let kind of representation stop her from making up new models. So she said, well, but I want edges, so give me some edges, I can do things faster. So in a work with her students, Mariam, Shankar, John, I forgot, sorry, Demis, right, and yeah, they came up with this model, and they showed that they can break lower bounds that were proven for the more restricted model. And of course, once Ronit thinks about it with students, and you think this is very basic, right? It's a very basic primitive. Why wouldn't be able to sample edges? Kind of, that's where all the things in graphs happening, right? If there's a lot of many isolated vertices, then it's just noise. Most of the time, we'll just see these isolated vertices. But if we have access to edges, that kind of directly we go to where things are happening in the graph. And also, there are many walks on random walks that actually kind of start with a random walk. Then after you do the t-mix time steps, you get a uniform edge. So it's really a very basic primitive, and it makes much sense to consider it. But of course, we needed to come out with it recently. But then, okay, we said, okay, we have this nice primitive, but there is representation, unfortunately. So we do kind of, how do we maybe simulate this query? So that was kind of the motivation for this work. So as I said, we want to be able to be epsilon close to uniform. So now we'll allow some noise. Okay, so now we are in the adjacency list model, and vertices are labeled 1 through n, and we can perform degree queries. So we can just ask what is the degree of these vertices, and we can sample uniform neighbors. And I'll try, I think it's a very short, cute result, and I think I'll have time to show you how we can get it. So this is the goal, but the goal is not to just sample one edge. Now we want to sample multiple edges. And why is that? Because really in Bonit's work and then follow-up works, it was used, these edge sampling algorithms was used to estimate some other subgraph parameters, but they needed many edges. And in the first work on sampling uniform edges, we gave a result for sampling one edge with probability n over square root m. And this is tight, but this is for sampling one edge. So we try to ask, well, and select what happened, but you need multiple edges. And this is kind of, if you need to multiply this by say you need k many edges, kind of this can become expensive. So we asked if this kind of naive idea of just invoking this single edge sampling algorithm k times, can we do better if we know that we need multiple edges? Yeah, so this is the kind of the first result showing that we can do a single edge in this time, which is optimal. And then we also focused on sampling edges. Here we showed we can also do it in time that depends on the arboricity. Then Tetek gave an improvement with Thorop, and finally we are able to do it exactly uniformly and optimally. But again, this is for a single edge, and the goal here is to sample multiple edges. Okay, so as I said, in the naive approach, we just invoke this algorithm k times, and we get dependency z on k. Okay, but what we show is actually we can improve this dependency to square root of k. So we don't need as many samples as in the naive approach. And also Tetek and Thorop showed that this is optimal. And I'll show you the algorithm first because maybe this is useful in case you want to sample multiple edges. It might be useful, but also I think there's some cute ideas there, which I think are nice as a nice like tool to add to your toolbox. So let me try to go over that. What's the algorithm? Let's do a warm-up. Let's assume that G is deregular. Then how would we sample an edge? All we can access is vertices and their neighbors. So first we select a vertex, then we query one of its neighbors. That's basically all we can do. And then we get that for each edge, the probability it is returned is 1 over n. That's the probability I choose this specific vertex. Then 1 over d, the probability I choose this specific neighbor. So for each edge, I get it with exactly uniform probability, 1 over n times d. So that's good. But then most of the graphs are not regulars. What do I do then? Then I can use some rejection sampling. And that's another useful technique because it makes things uniform, and uniform is good. So what do I do here? Again, I have a graph, but this time it's not regular, but I know it's bounded. It has maximum degree d max. So again, I sample a vertex, then I sample one of its neighbors, but then I do one more step of rejection sampling, and I only return it with probability dv over d max. So now I get that this every edge, okay, this specific edge vu is sampled probability 1 over n that I sample v, then 1 over dv that I sample u, then I only return it probability dv over d max. So I get 1 over d max. So you see, kind of, if I didn't have this step, then I would get this bias because of the degree of the originating vertex, right? I get bias towards edges that are incident to vertices with low degrees. But this kind of cancels this bias out, and I get uniform. Okay, good. But what if Dmax is kind of high? Then that's the idea for the following thing. What we do is, we just need to notice that every edge is returned with same probability. Okay. And what do we get for the sample complexity? For each edge, this is the success probability 1 over n Dmax. So overall, the success probability is m over n Dmax. So we just have to take the inverse. We need to repeat n times Dmax over m to get an edge. Okay, so that is good. If Dmax is low, it's good. If Dmax is high, it can be as high as m, then that's bad for us. So let's see, what do we do about it? And just to say that throughout the algorithm, I think about each edge as 2 edges. So VU and UV are 2 different edges. That just makes things simpler to think about. So I want to be able to sample both VU and UV. Okay, so what does the algorithm do? It partitions the vertices into light and heavy according to some threshold. Sorry, it's theta, not T. So if it's below this threshold theta, then I'm calling it light, otherwise it's heavy. To sample light, we did exactly what we did in the previous slide. We just select a uniform vertex, and we return one of its uniform neighbors with probability dV over theta. So now it's not Dmax, but it is true that for all vertices that are light, their degree is at most theta. So I can just, instead of Dmax, I just do theta to replace it. Okay? And then each light edge is returned with probability 1 over n theta. So again, it's uniform, and we're happy, but these are just light edges. What do I do about the heavy ones? Okay, so here I use the fact that I know in advance that I need multiple edges. So I'm kind of allowed to spend some time in the pre-processing and then to be able to sample these edges fast, okay? And I added this, so like for one edge, I need n over square root n, but if I need multiple, then I can do some amortization. And the amortization is that I do a costly pre-processing step to get faster edges. So what do I do in the pre-processing step? We sample a uniform set of vertices size n over theta, okay? And then we can build a data structure that returned each one of these vertices. I just sample a bunch of vertices. This is S, okay? And then I build a data structure that allows me to sample one of the incident edges to the data structure in time O of 1. Okay, then to sample a heavy vertex, I sample one of these edges uniformly at random. I sample one of these edges, don't worry, I'm almost done. And then I get to some vertex W. I sample VW, and then if W is heavy, I sample one of its neighbors uniformly at random. The complexity is n over theta. And let's see what is the probability, and this is, I think, the last slide. What's the probability that this W is returned, right? So when I sample the edge, I get to W if initially the edge that I sampled from ES, let's call it, touches W. So how many such edges are there? There are exactly the number of neighbors of W in that sample over the total number of edges. So we have these many neighbors of W in our sample, a V in the sample, and this is the size of the sample. So this is the probability we reach this heavy vertex W. Okay, I think there's something wrong here. Okay, and then I take one more step. So what's this probability of VU? Okay, so it's the probability I reached V, then 1 over dV. But what do we know about this set S? That it kind of, because W had V had at least theta neighbors, and I took a set of size n over theta, it captures the number of neighbors of V. So this behaves as expected. So what is the expected? For each vertex, it's a neighbor of V with probability dV over n. And we have S vertices in the set. So the expected number of vertices of neighbors of V in the set, it's dV times S over n. Also, and we need to, this sample space is E of S, and we have S vertices. And the sample is large enough, so again, it will be as expected. So for each vertex, its expected degree is just the average degree, it's m over n. So what we get is that these two cancel out, and we get dv over m times 1 over dv. There's removed some normalization factor, and we get again, 1 over m. We actually get 1 over m, the probability that we sample this edge that is incident to VU. And again, this is uniform. Yeah, so, and the time complexity for this was due to the pre-processing. It was n over theta. And that's it, actually. Now we just kind of balance the two costs. We have one cost that comes for sampling the edges. It's k times this factor. Then we have the pre-processing. And if we kind of just make them, make them equal, we get this square root k over n over square root m. And then also this is optimal by a result of theta and zero. So that's it. And thank you very much, Ron.
There's a restriction on k, right? Theta cannot be too large, so at some
Theta must be at least square root m. So yeah, k, no restriction.